All right. Today I want to go ahead and improve the performance of our game, especially since not everyone is going to be uh, either developing or playing the game on, a computer as powerful as this one. So right now we're using about 65% of one of our CPU cores just to run this very simple game that isn't doing a whole lot, right? Like OBS is recording everything and writing it into a video, and our game is taking almost as much time as that, which isn't a great place to be in. So the reason for that is our game is just running as quickly as it can. It's getting input as quickly as it can, it's rendering as quickly as it can, and it's never even bothering to go ahead and just slow down a little bit and wait for something else to happen. So, what I want to go ahead and do today is introduce the notion of time into our program. So, this is pretty important. Really, all games are going to want to do this. We want to know, the time that we started, how long we've been running, how long it's been since we've drawn something, and that's just for the sort of like low-level engine stuff. We're also going to want to know that for gameplay logic, right? We want to know, hey, how long has it been since I drank a health potion? How many seconds or how many meters per second do I run? Things like that. So we're going to include this file, which is the Unix standard.h, and that is going to give us a couple of things which we can use. I'm going to quit our game right here, which we can use to start keeping track of time. So there is a thing called a time spec, and this stores the number of seconds and the number of nanoseconds, and it stores them as integers, right? So we are going to want to populate that. So, because we have a struct right here, but we haven't filled it with anything. And we are going to use this function called clock get time. We're going to pass it in this macro value, and then we'll pass in the address of spec. Clock monotonic just means, it's monotonically increasing. It's increasing by the same amount every time. I have honestly never even looked at other things I could be passing in to get time. That seems to just be the thing I always want to do. So this gives us the number of seconds and nanoseconds, and they are under TV seconds and TV in seconds, right? And we want to go ahead and use these two numbers and sum them together such that we get the time in in milliseconds. So that is going to be something we want to store in a real number, right? Since we have these two integers that are storing different parts, we want to combine those together. And that means that the nanoseconds is going to be the fractional part, and the seconds is going to be the whole part, right? So we are going to say the time that we started, and that's going to be spec.tv seconds. And we are going to multiply that by 1,000 because there are 1,000 milliseconds in 1 second. This double right here, it's like a float. It's a real number. It's just 64 bits instead of 32 bits. The reason we want that is when we're using integers, if we increase the size, if we say that we go from a 32-bit to a 64-bit integer, we have more bits to represent more numbers. So our maximum size just gets bigger. With real numbers, one of the things that it does for us is it allows us to be more precise with our calculations. So that's a little beyond the scope of this video right now. We may get into that in the future. If you're interested, you can go ahead and look up floating point precision. There's a lot of stuff, but essentially, we can't represent real numbers exactly. Think about 3.3333333, etc. Right? We can't represent that going on for eternity, and there's other things of that nature. So what we do is if we increase our precision by using 64 instead of 32 bits, then we at least are more accurate, even though we can't be infinitely accurate. So we're going to take that 1,000. So the number of seconds times 1,000 will be the number of milliseconds. And then we're going to get the fractional part by saying we're going to take the number of nanoseconds, we're going to divide that by 1.0 e to the 6th, right? And that's going to be a million. If you've never seen this this notation before, this is like exponent, and this is 6, so this is going to be like 1.0 times 10 to the 6th. So 10 to the 6th. So we're going to move that decimal place 6 places over, and we're going to get a million. All right, so now I am going to create this thing called system time. And we can just say that it equals start time. And I'm going to also have this thing, I guess, called game time, which is going to start out at 0. And then I also want to say we have a thing called previous system time, which we can start out setting it equal to system time. And every time through when we're running, we are going to do this part again. But rather than changing start time, we're going to set the system time. And we are going to take the previous system time and set it equal to the system time before we change that value. And we can go ahead and say that our game time is going to equal system time minus start time. Now, the value of start time is, again, it's going to be in milliseconds, and it's milliseconds since the epoch began. And on Unix or a Linux operating system like we're using here, the epoch began January 1st at midnight in 1970. So it's the number of nanoseconds since that happened, I believe. Now that I think about it, maybe get time is going to give us the amount of time since our computer was started, but I'm not actually sure. Okay, yeah. It cannot be said. It represents monotonic time since some unspecified starting point. So maybe that has nothing to do with the epoch. Clock real time is the number of seconds and nanoseconds since the epoch, which again would be January 1st, 1970. But we aren't going to care about that since we're using monotonic. Okay, so let's see, where was it? Oh yeah, one more thing we want a variable. We'll call this delta time, and we don't even care what it is initially, but we will say that delta time is going to equal our system time minus our previous system time. So delta time will be representing the amount of time that has elapsed since the last frame. And here, a frame is everything between our while loop, right? Because what's happening is we clear the screen, draw some stuff on it, clear the screen, draw some stuff. And each time we clear and then draw is one frame. So our delta time is the amount of time since the last frame, right? And again, that's going to be in milliseconds, so it would be like if delta time was 16, that means it's been 16 milliseconds. I'm also going to make a variable. I'm going to call it dt, and this is going to be delta time divided by 1,000, because I want to also have delta time as a fractional part of seconds. And we may see later on how we care about that. Uh, when you're doing calculations like for animation and you're like scaling things, so you're like, oh, you have an animation that's moving a point A to a point B, right? And you want each frame to move a little bit along that. Well, it's easier to do that, just, the numbers are smaller if our delta time is much smaller. Whereas if you're moving 1 unit times delta time, and delta time is 16, then every frame you're really going to move 16 places, right? Whereas if delta time is very small, it's just, it's a smaller number. It's easier to sort of think about that and keep our units reasonably small. So that should be it right there. We can go ahead and throw these up. I'm going to say, we're just going to say print delta time, like that. This LF stands for print long float. So that's, a double. It's a float that's long. It's 64 bits. So, oops, I see right away. All right. So our values are, it looks like they're between like 2 and 5. So on average, we're taking about, 5 milliseconds, or probably an average of like 3 milliseconds, right? So that's really fast. Most games are going to be running at 60 frames a second, so that's going to be about 16 milliseconds per frame. So we're running, about 8 times as fast as that. Sometimes we're running like a third of that. So what I want to do to go ahead and improve the performance of our game is just say, hey, if it hasn't been enough time yet, don't render. Don't draw anything. Don't waste CPU time just, drawing things that we don't need to. Because a human isn't going to be inputting characters into our game necessarily at a rate of like 1 every 2 milliseconds, right? Maybe if we were doing like a pro Dota esports type of thing, maybe we would care about input being that quick. For our turn-based game, though, we don't really. And plus, we're running on computers that probably aren't as powerful as something you would be using, in an esport context. If we do wind up caring about that later, we can go back and revise this code. But right now, I just want to get the simplest thing that gives us the biggest gain. So I want to bring us just down from using 65% of the CPU. If we can use any less than that, I think we'll be in pretty good shape. So what I want to do is keep track of this variable. We'll call this time since render. And we're going to say that it equals 0.0. And we're going to say that every time we render, every time we do this x put image, we have, our time since render becomes 0, right? And we're going to say that if our time since we've rendered is less than our frame rate, so let's go ahead and say double frame rate, and this is going to be 1.0 times 60.0, so this is in seconds, which is hertz. So hertz is the number of oscillations something does in a second. So we are, by doing this with our frame rate, we're saying, hey, we're going to render 60 times in a second. And honestly, we can just go ahead and say 30. Like, we're not a fancy Call of Duty or Halo or PUBG or whatever. I think rendering 30 times a second is probably okay. Especially, again, we might be on a Raspberry Pi, so that's a pretty good frame rate. All right. So yeah, what we're going to want to do is say, hey, if the time since render is less than our frame rate, then we should just go ahead and sleep until we know it's time to render again, right? And the way we are going to want to do that is say, okay, at the end of our loop, right, we're going to see how long until we should render again, right? So we're going to say if time since render is less than our frame rate, then we are going to use this function which is called uSleep. This is going to tell the CPU that, hey, this program that's running, it doesn't need to do anything right now. You can go ahead and, slow down, stop trying to compute things as quickly as you can, and just go ahead and rest. And this is going to take microseconds. That's a thing that I know. If you wanted to, you could go ahead and look it up. You could say, look at the man page and see, it suspends execution of the calling thread, which is our program, by some number of microseconds. So let's go ahead and say that our time until render, so the number of milliseconds until we are going to render, is going to be our frame rate, because again, we know that we're smaller than our frame rate. It's going to be our frame rate minus our time since render, right? So if the time since we've rendered is going to be 0 seconds, right? Then we know, or 0 milliseconds. Then we know, hey, we can sleep for 16 milliseconds until we need to go ahead and wake up and render again. So this is going to be time until render times 1.0 e to the 6th. Because I believe there are a million microseconds in a millisecond. So we will go ahead and sleep and say every time through here, we're going to say, right here, this is going to be time, what is it? Time since render is going to be plus equal the delta time, right? So this is dt time since render and frame rate are in seconds, right? Delta time, system time, game time, start time are all going to be in milliseconds. So I'll go ahead and put that up. Seconds and seconds, right? And then what we want to do, actually, we'll go ahead, we'll put this up right here. We will put this right here, right? And we're going to say, all right, hey, go ahead and sleep. And when you wake up, we'll know that the time until render is going to equal 0.0, right? Or sorry, not the time until, the time since render, right? So if this is 2 milliseconds and our frame rate is 16 milliseconds, here we're going to get 14. We're going to say, all right, convert that into microseconds. Sleep for 14 milliseconds. Now that you've woken up, now that you've moved to this part of the code, we're like, all right, hey, we know that it's been, essentially 0 seconds since you've rendered. we could probably go ahead and move this down here to just make it more accurate and say, all right, now that we've rendered, we know it's been 0 seconds, right? Um, Go ahead and keep in mind, this isn't the most robust way to do this. This is not what you would want to do for like a physics-driven, real-time video game. Maybe later on, if we add animations into this game, we will go ahead and want to do it that way. Um, so if you're curious about like the proper way to do this or the robust way to do this, go ahead and email me and we can talk about it. I just, I don't want to spend too much time harping on this since I think there's more interesting things we can do for the game. We won't really even notice much of a result here. Well, okay, so you see now our frame rates are much, much higher, right? About 30 milliseconds. Sometimes it looks like we're getting these spikes where it's very low, right? Where it's like 4 milliseconds, 2 milliseconds, right? Let's go ahead and hop in to right here and see what our word game is now. So now we're only using 10% of the CPU, so we are 5 times faster than we were earlier. And I think that is a pretty good place to be at. So, yeah, I can type hello, I can type the, I can type dog, cat, right? And it doesn't look like I'm like losing any input, right? If I say put, right? Because, if we went ahead and let's say we dropped this down very low, right? Let's say we run at 5 times a second, right? Well, for one thing, we are going to be pretty efficient. Like our 2.6 of the CPU, right? The issue there, though, is that that's so slow that, we kind of have to type like this. Because if I type just THE, it dropped the E, right? Because it like wasn't rendering at the right time. So that is not good at all. Let's go ahead and bump this back up to 30. Again, I mean, if you are a slow typer, it's probably not going to matter, really. Like, again, typing multiple characters in won't be as big of a deal. But we'll go ahead and keep this at 30. If it's running slow on your computer, that is, feel free to lower it. So now I'm going to just take out the print statements because I don't really care. I don't care what the milliseconds are so much now anymore because I know, that we're being performant enough, or at least reasonably performant enough. And I also don't want to spend the time drawing things to the terminal, right? But you can see that we aren't really getting a very even frame rate. We're sort of oscillating between like 30 milliseconds and 4 milliseconds. So, again, this is not a very robust way to go about this. But in the future, I think we can go ahead and improve that. Maybe once we have more interesting things going on in the game and we start caring a little bit more about how long it's taking to draw things, and we start caring about, drawing things like animations at the right times.